Yeah, ik had, before the break I started to be a bit chaotic with indices. That's completely my mistake. Next week I will be more precise in that. The main thing is sometimes you repeat an index, and well, if the whole goal is repeated indexes are used for summation, then you sometimes get into trouble. But we always can substitute one index for another one, and you can use k instead of l or m or n, as long as they don't go out of the equation. We call them dead indices when the summation is within the equation. My notes are a bit sloppy in that sense. The book is very precise in that. So if you want to know, well, how does it work with the I, J, K, L, M, N, it's all in the book. And that's all I wanted to say. Yeah, and then I had a question during the break. Why are we just doing a small variation on every time? Because every time this double pendulum and this method and that method and in the end you will be able in this course to find motion for a three-dimensional multi-body dynamic system which is constrained. So find the motion, not the acceleration. Yeah, of course the acceleration, but the motion, integrate the equation. That is the whole goal. And since all systems have different peculiarities, sometimes one method is a lot better than the other one. So therefore I like to give you a toolkit with a number of methods. Like you can do it like this or you can do it like that, and it all depends on the problem at hand. And you can compare that with a toolkit and a number of screwdrivers. You have a flat screwdriver and you have a screwdriver with a cross head or with a hexagon thing. Of course you can put the hexagon in the cross one, but that really doesn't work. So I try to give you a set of screwdrivers to fix all the different problems. That's the idea. Okay, back to today. The TMT methods. Let's see how it works on an example. And as an example, I'm going to take the same one from last week. That was this load swing problem, right? So what was the load swing problem? We had a cart which was moving in a horizontal sense, and hanging from that cart was a mass. And now let's say it's like a rigid body here. So it's really glued in here. And so we have a rigid body here. So we have mass and we have inertia here. How did we, oh yeah, we had generalized coordinates, right? So I need a coordinate system. So I need to say this is x, this is y, and my rotations are like this. Then I need a generalized coordinate. No. First, I have 1 point mass with an x, y, and phi coordinate, right? So my COM coordinates are this xi being x, y, and phi. Just simple, one rigid body. Of course, there's like, hey, you can say, oh, there's a constraint, yes, but we're not going to express the constraint. We're going to use generalized coordinates. And I take S, and what did I do? Alpha, I think, yeah. So for our generalized coordinates, I choose this Qj, and I take S and alpha. Now, most of you are really smart, right? Is everything did I not forget? Yeah. So most of you are really smart. So we can immediately write down what our generalized forces are. Yeah. So our QJs, we can immediately interpret them as, oh, if I have an S here, then it should be some action-reaction force. So I'm tempted even to draw it into the figure. Although in the spirit of Lagrange we don't need all these drawings, but it's sort of nice from an educational point of view now to say, oh yeah, we have this, and then this generalized force is of course this linear force moving back and forth. Likewise, if this is alpha, and if it's with respect to the inertial world, then you have a torque apparently here, m alpha, and that same torque is then on the ground, m alpha. It's an action-reaction torque, and actually every force is an action-reaction force. I mean, a force is never alone. So let me repeat it. A force is never alone. It's always what Newton says. If we think, oh, gravity is pulling on this thing, yeah, but the thing is also pulling on the Earth, right? It's always pairs. They always come together. Okay, so length L, we have gravity here. What else? We have mass, we have inertia. Yeah, according to Heike, I have to put in this force, mg. Anything else? Are we missing anything? No, I think that's it. Yeah, that's the problem defined. So then for the TMT method, what do I need? I need this mapping. I need to express my coordinates xi in terms of this transformation in terms of my QJs. Or in other words, the x position of this center of mass is, well, this s plus this distance, so that's s plus L sine alpha, right? Is that correct? Yeah. The y position of this guy, it's negative minus L cosine alpha, right? The orientation of this body, phi, well, it has to do with this angle alpha, but well, let me write alpha minus pi over 2. Just to say, well, the horizontal case is the zero case. It's not essential, but it's to show that it's this mapping. Okay, what do we need for the TMT method? Now let me again repeat the equation. So we need Ti, comma k times m and ij, I need to use a j, tj, comma l, q dot l should it be, that's the l, and this j goes with that one. And that's the generalized forces, qj, plus the ti, comma k, fi, minus m, I, well, and m to be hm, to be that short. And to be specific, this hm is this t, m, p, q, q. Oh, the p, that's not smart. That's not smart. Rs, q dot r, q dot s. And now there is a spec here. Get rid of that guy. Yeah. So as you see, you can just make up these indices as you go along. Okay. Now we have defined the transformation. So the only thing is we need Jacobians. Oh, we need a mass matrix. Well, in any way, the mass matrix is super simple here. Mij is just a diagonal m, I. So that is super simple. What else do we need? Well, we need this Jacobian, this Ti, j is, well, as a matrix we also need it, because we have to do this matrix multiplication. Oh, maybe it's nice to write this also as a matrix. M, M, I. Zeros. Okay. The Jacobian. So we have to take this expression. So we get 3 rows and we have 2 variables and 2 columns. So first the first row is differentiate with respect to S. So that's a 1. And then differentiate with respect to alpha. So that's going to be L cosine alpha, right? Then the second equation we have to differentiate with respect to S. So that's a 0. And then with respect to cosine alpha, that's minus sinus alpha, so minus, 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 becomes plus L sine alpha. And then the last one we have to differentiate with respect to S again, 0, and with respect to alpha, that's a 1. Yeah. So that is this Jacobian thing. And you can read it like this. You can also say, no, I find it a lot easier to first write down what are the speeds and then look at what the multipliers are for the different speeds. So you could also say, no, I do it this way. X dot is S dot plus L cosine alpha times alpha dot, and Y dot is L sine alpha, alpha dot, and phi dot is alpha dot. And then I'm going to write it as a matrix equation, y dot phi dot equals matrix, and then here S dot alpha dot. And then the answer is, of course, totally identical with what I already have. It's just this Jacobian times d speed. There should be a dot and S dot. So, as you like it. I mean, either cook up immediately the Jacobian or write down these speeds and write them like that. So this is, we have this term. We have this term, Qj. For now we're not going to apply any generalized forces. The only thing is these Fi's. So we do have applied forces on the system. In the x direction there's nothing. Oh, I should X no force, in the Y minus mg, and there are no torques. So 0 minus mg, and there are no applied torques. So then we have covered this guy. We know the mass matrix. Oops, now we need this thing. And there are various ways to do this. You can take, you could take this Jacobian and then, like it says, multiply it with the speed and differentiate it again and so on. Personally, I always find it easier to take this expression and to neglect all the things with the double dot. To think, oh yeah, the double dots I already have covered. I don't have to do that. The only thing I'm now seeking for is that I have to differentiate this with respect to coordinates and then times speed. So these this x double dot, if I do it, then the first step I take is s double dot, this guy, plus this constant times this guy, plus L cosine alpha, alpha double dot. We already did that, because we already have the Jacobian. So you don't have to do that. That's sort of double work. The next step is, oh, but it's also a function of the coordinate, so I have to differentiate it with respect to the coordinate times the coordinate speed. So, and in this case, the only coordinate dependency is alpha, so I get that it's becoming a minus, not a plus here. So go away. So differentiate this with respect to the coordinates becomes minus L sine alpha times alpha dot, and we already had an alpha dot. Yeah? And there are no other dependency of, there's no dependency on S, otherwise you also have to do with respect to S times S dot times alpha dot, etc. But that's not there. Okay, then the next step, this one, Y double dot, well, nothing. Of course, first we keep this constant, but again that's double work, because this is already stated here or here, whatever you want. Oh, 100%. But now we have to take with respect to S and alpha. Well, it's not a function of S, so there's nothing. And with alpha, we get cosine alpha, so we get L cosine alpha, alpha dot, alpha dot.
Double dot on the first alpha?
Yeah, double dot, thank you. Yeah. And then the last one, phi double dot, is just alpha double dot, yeah, plus 0. There are no dependencies. So these guys are now this Jacobian, this Ti comma j q double dot j, and these guys are this Ti r s q dot r q dot s, or in other words hi. This is just one vector. This stuff. So combining that, so my hk is apparently 3 units. It's the minus L sine alpha, alpha dot squared. It's the plus L cosine alpha, alpha dot squared, and it's a 0. Yeah. And now I'm in business. Now I have all the stuff I need. I have my Jacobian, I have my mass matrix, I have a Jacobian I already had. I have these strange convective terms. So now I can cook up the whole thing. So let's first make this mass matrix. So we want to make the Ti j m I k t k l, right? Or in matrix notation, T transpose m t t. That's the guy we want to make. Now we have to copy the T stuff, right? Oh, that's sort of easy. I can sort of remember that. It's a 1, 0, 0. The first was the L cosine alpha, right? The second was L sine alpha, and then 0. Then we have to take the transpose of the matrix, right? Then we have this mass matrix, M, M, I, and then we have to put the transformation matrix here, 1 L cosine alpha, 0 I L sine alpha, 0. This should be a 1, this guy. 1, 0, 1. Now, whatever, as you like it, you can first do the multiplication of this times this, and then take the transpose of this times the result. There is a quick and dirty way, because this is only a diagonal, right? Meaning that such a diagonal matrix only changes every row. This row is multiplied by m, this multiplied by m, and this row is multiplied by I. So eventually the result will be m, and here ml cosine alpha. And this is 0, and this is ml sine alpha, and this is 0 and I. You can also do it by head, but for now let's write it out. And then the last one is we multiply this with this, but we need to take the transpose. So normally you would say row times column, but now it's super easy. It's column times column, columns times column. Okay, and then the end result is, well, let's put it underneath, that's a bit more space. So this times this is m. This times this is ml cosine alpha. This times this is, UP, ml cosine alpha. Why do I say UP? Is there a UP in the audience?
Symmetric.
Yeah, symmetric. I'm happy because I expect a symmetric matrix. Because why is it symmetric? Well, if you take the T transpose MT and you do the transpose, what is the answer? Then you get T transpose times M transpose times T transpose transpose. Or in other words, T transpose, and since M is symmetric, M T transpose. Hey, it's identical. So it should be symmetric, right? Now the last one is this. Ooh, so that is ML squared cosine squared alpha plus ML squared sine squared alpha, so this and then plus I. Well, everybody knows that cosine square and sine square is 1. So finally our answer is ml cosine alpha, ml cosine alpha, and here ml squared plus I. So that's our mass matrix. Yeah. Then we need the right-hand side of the equation. So again, we need the Jacobian. So the Jacobian was is 1, 0, 0, L. Maybe I do a shorthand notation: cosine alpha, sine alpha, 0, times. Well, it was first the applied forces, right? And those were nothing in the x direction, minus mg, and nothing in the phi direction. Then minus a mass matrix, this mmi, times these convective accelerations, and I don't know by head what they were, these guys, sin cosines here, minus L sine alpha alpha dot squared, L cosine alpha alpha dot squared, 0. And then close the bracket. That is the right hand side of the equation. Yeah, you could say plus, and then I have these two applied forces, Fs and M alpha, my QJs. And this should be transpose, of course. Now again, super easy, when you have to do transpose matrix times. This is just row times column times column. So the answer is, so the first answer is 0. And this times this is zip, nil. And then this times this guy, I get minus ml sine alpha, mgl. mgl sine alpha. Okay. So that's this first term. Then I have to do this second one. And I'm not going to multiply this out first. I know, of course, that this goes with m, this goes with m, and the 0 goes with I. So the only thing I have to remember is, oh yeah, I have to do this times this, and remember I have to multiply with m. So minus, let's keep the minus for now, and then we get, so the first times this one, so that's minus ml sine alpha alpha dot squared, right? This guy times this guy, n with an m. Then this guy times this guy with an m. I get first minus ml, what do I get? Cosine alpha times sine alpha, cosine alpha sine alpha, alpha dot squared. Then plus m l sine alpha cosine alpha, alpha dot squared.
The L squared.
Yeah, L squared, LL, thank you. And that's also on the top, Yeah, thank you. And then finally I have my Fs and M alpha. So these are the forces on the right hand side. Now maybe I made a mistake because these cancel out, right? Yeah, maybe. Did I, my signs are right? Yeah, minus plus, it's a minus. No, that's a plus plus. Should be right, I don't know. Well, I do know, but we can later explain why they cancel out. By the way, notice that from a three-dimensional force world we go to a two-dimensional, so it looks like a projection we are doing. Okay, let's combine our result, because now we're done. We have a mass matrix, ml cosine alpha, ml cosine alpha, and then ml squared plus I. This was the mass matrix times this acceleration, s double dot alpha double dot, equals, and then we have fs and m alpha, and then non-zero terms are plus m l squared alpha dot squared sine alpha, and the other one is just gravity, minus mgl sine alpha. So these are just the equation of motion in terms of these generalized coordinates. It's always good to check your work. So the first check we could do is dimensions. So if we look at the first equation, that's the force equation, right? So this is mass times acceleration. So this should be a force. Well, this is an angular acceleration. This is mass times distance. So this is a force. So that's correct. And on the right-hand side, I have a mass times, this is acceleration.
That's velocity.
It's velocity, yeah? But so should it be L squared? Is that correct? Did we make an error somewhere maybe? So where does this term come from? That's the first times this guy. Ah, yeah, there shouldn't be, this is incorrect, eh? Hoopla. So you see, it's always good to do checking of units, because then you get your small errors out of the way anyway. So this guy times this guy times this guy. So there's only an L there, no L squared. And of course, this is sort of a centrifugal acceleration. It's angular speed times the distance. Omega squared r, something like that. We will look in detail later on. So now the units are right. Signs I don't know, we'll see. Second equation. So this is mass times distance times angular acceleration. So this should be something like a torque equation, right? Well, we have a torque here, so that's right. Here we have mass moment of inertia times angular acceleration, that's good. So this should be a torque. Well, this is a force, mg times the distance L, that's a torque. Okay, but now we even like to interpret why are these terms gone? Is it correct that the signs are out, plus and minus, and why do I see here an alpha dot squared, and why do I not see an alpha dot squared? And to do that, we have to go make a drawing again, of course, of our problem. What was it? This distance S, and then from this distance S over an angle alpha, we have here our mass at a distance L. And to really understand the whole dynamics, we have to put in accelerations and D'Alembert forces, right? So we have to, in our mind, think, oh yeah, if we want to check numbers here, we have to do this mind game, like let's put a constant acceleration on the system and keep the angle keep this mass at a constant angle, but let's accelerate the thing. Oh yeah, that was not the meaning. Yeah. Let's accelerate the thing with a constant acceleration to the right. What does it take to do that? And then of course it should be in the first equation. So it tells you, oh yeah, the force you need here, this Fs, is this linear acceleration times this mass. Well, this is 0, because we keep the angle constant. So what does it take? Well, it's this mass times the acceleration. Well, that's okay. If there's a certain mass, then just mass times acceleration to make this linear motion. Then you can also do the other thing, like, okay, let's assume there is some angular speed here. Well, if there is an angular speed, then we know from experience that there is this angular, this acceleration, this centrifugal one, right? What is it called? Alpha dot squared times L. It's an acceleration inward. Moreover, you could say, well, why not draw all the accelerations in there? Then this should be alpha double dot times L, perpendicular to this one. And if this is moving with S double dot, then this should be S double dot. So now we have all these accelerations, and now we can do the game of D'Alembert and say, oh, then apparently the forces are mass times this acceleration with a minus sign. So we can make like a force diagram out of this. So we have this mass, and then we have here mg working on the thing. Then we have apparently, in the spirit of D'Alembert, a force here, which is m alpha double dot L, right? And then in the spirit of, again, we have a M S double dot, and a force here in this direction, which is M alpha dot squared L. Okay. At an angle alpha, yeah, and at a distance S, and this was L. And now with this in mind, we can look again at the equation. And we can say, okay, if these are our forces, how do they contribute to the different motions? For instance, we want to check this contribution. So apparently, if we look at the linear motion, this force, this D'Alembert force, has a contribution to this linear motion. And yeah, that's correct. We have here this M alpha dot squared L, but not the whole force. We need the projection of that. And what is this projection? That's exactly this M alpha dot squared L sine alpha. So that's exactly this term, of course, in the linear motion here. Which term do we also want to explain? Well, maybe we want to explain this term. That's sort of easy. So this is the alpha equation. So we're talking about torques about this point. So which forces are delivering torques about this point? Well, of course, this guy, but it's on the other side of the equation. This guy, well, only the projection of that guy delivers a torque, right? This one is in the length of the length of L. So for this motion it doesn't work, but only this part. And that's exactly this mgl sine alpha. And you see, if this is plus alpha, then that's against, in the opposite direction. So this is clearly this mgl sine alpha. So we have explained this term. Then you like to explain these terms. Well, this one we already did, right? This is a sort of a magical one, which I like to rest for now. Let's first start with this one. This is just, I have an angular acceleration, what torque does it take? Well, I have a mass here, and at the center of mass I have a mass moment of inertia, but the point of rotation is here, at the center of rotation, because I'm not moving the whole thing, so the center of rotation is here. Then the mass moment of inertia is this mass moment of inertia plus distance squared times mass, so that's exactly this term. So that's also explained. So we have explained this one, this one, this one, this one. Now I want to explain why this disappears. Where does this come from? Well, here we had this convective acceleration, right? And the convective acceleration we can immediately draw in the figure, because this is an acceleration L times alpha dot squared in the x and y direction. So in the minus x and in the plus y direction. So what is that? Well, if you look at the figure, we see that's exactly this acceleration, of course, with a minus sign and a plus for the cosine. So that's the centrifugal acceleration. Well, does the centrifugal acceleration, this term, does it contribute to this? No way. So in the second equation, this guy by this Jacobian is cancelled out. And that's what I mean with projection. So projecting that force, this force on this motion, completely drops out that force. Okay. What else? Yeah. This guy. So what is this guy? Then you have to really look at the equation, what you are doing. So you are looking at the equilibrium or the dynamic equilibrium in the motion of S. So forces in this direction. Yeah? But you are not moving the thing, because we look at this term, but you are looking at forces in this direction, but you are rotating the apparatus. So you keep this stationary, you give it an angular acceleration, and then the question is, what force, linear force, do I feel here? Well, then you just have to look at your diagram and say, oh, for this acceleration I have this D'Alembert force, yeah? And if I have to project that on the horizontal, I have to take this part of this D'Alembert force, and that's clearly M alpha dot L cosine alpha. And that explains that we have here an ML cosine alpha in this mass matrix. So that's the cross term we actually have. And by that we have explained all terms in the equation. And also the method. And I'm done for today. What is the time? Oh, 10 minutes. See you after the break. Success with the exams. You can do it.